today we will have three short presentations that will start to delve into the vascular metabolic indices as they relate to Alzheimer's disease or related dementias. And I will start off first, and then we'll have Mike Bancks go next, and then Chris Schaich, and I'll give you a little bit of the overview of what the topics are that you've for today's session, and also a little bit of the rationale. So this is really a new series that we're launching with BRAAIN. This is a very in-depth, complicated series of topics where we are interested in pursuing new measures that we can integrate into our ongoing cohort and clinical studies in the ADRC. And this has started as a discussion by the BRAAIN Planning Committee about how we might bring in some speakers to talk about some of the existing measures and more of the cutting edge measures that are being developed that relate to vascular metabolic indices. So today really sets the stage, and that's my portion of it. I know all of you, but I'll just introduce myself if someone's on the call who doesn't know me. I'm Tim Hughes. I'm an associate professor in internal medicine, gerontology, and geriatrics medicine, and a member of the ADRC, and one of the presenting on behalf of the BRAAIN Planning Committee to set the stage for what we're hoping to accomplish with this series. So what's the origin and why are we having this series? Well, it comes in line with the themes of our ADRC. As you may know, our ADRC is focused on the vascular metabolic risk factors that may predict conversion from normal cognition to mild cognitive impairment and then to dementia. And we have a lot of vascular metabolic measures in our studies currently. These include things like standard seated blood pressure measurements, arterial stiffness measurements, metabolic measurements such as hemoglobin A1C, oral glucose tolerance test, and we'll also be adding in the near future additional measures that relate to electrical impulses of the heart and also continuous glucose monitoring. But it's really come to prominence that we recognize that we need to further leverage some of the existing data that we have related to vascular and metabolic data, but also to expand our repertoire. There are a lot of resources in our ADRC that can be used to develop new metrics, new measures, and new indices that will help us further characterize vascular and metabolic risk factors for ADRD. So this series is going to be in two parts. Today is going to be the first part, talking about existing vascular and metabolic indices in the ADRD. And then part two will come up in spring, and that will be looking at more novel indices of vascular and metabolic health. And for this, we would love your input, and I'll make a call at the very end for additional thoughts on speakers and topics of novel indices of vascular and metabolic health. So first we need to set the stage. What are we talking about? What are these? Is it indexes, indices? It depends on where you're from and which way you want to spell it. But essentially, how is that different than a biomarker? So many of you know biomarkers are a way to say biologic markers. These are individual measures that are unidimensional. And if you think about it, a measure like cholesterol, a measure like blood pressure, these are individual metrics that in and of themselves measure an aspect of physiology. And they may be markers of a condition, but they alone have units because they are a measure of a physiologic piece that we're trying to look at. But sometimes those aren't enough. And an index itself is a compound composite measure, which aggregates multiple measures together that are used to further understand the extent of a condition, to possibly define a larger phenotype, and can be used to define not just the individual measures themselves, but the aggregation of those measures into things like vascular risk scores. So one of them we'll talk about today is the Life Simple 7 that you may have heard of. It's the American Heart Association's version. There's also polygenic risk scores that are not looking just at your risk for developing a disease based on one gene, but also your risk for developing a disease based on multiple genes or characteristics of your demographics that may also increase your risk. So in the cancer world, these are models that are used all the time to figure out risk based on age, the presence of having specific genetic markers for a disease. And these are often for complex disorders that may not be single gene focused. A really great example is this metabolic disorders. Metabolic disorders are integrally linked with vascular disorders, and they share a lot of the same risk factors. And it's really hard to understand the breadth of a metabolic disorder, just like a vascular disorder, if you're looking at one aspect of a condition. So oftentimes these are brought together because, getting on to the next piece, is no single measure often predicts a complex chronic disease very well. There's residual variance, as we say in statistics. You're not predicting a lot with one individual measure. But when you add those measures together, you follow these principles that have been very well established for multiple fields. Neuropsychology is a perfect example, and we'll talk a little bit about that, and cardiovascular disease. It's under the premise that risk factors are aspects that may be impacted. They come together to bring a broader understanding of one's risk for a disease, and these may be modifiable risk factors or not. They can be used to manage both risk and care, and they can also be used in and of themselves as targets for a specific aspect of the disorder. When you have a single factor alone, it gives a single prediction. If you're not used to seeing these types of curves, these are called receiver operating curves. And at the horizontal line, it's a 50-50 chance. Using this measure across all of the individuals who have this measure, how well does it predict being a case of the disease or someone who does not have it? And in this case, when you have an individual measure, it oftentimes gives you these ROC curves that are just pretty close to that major line in the middle. Really, it's a 50-50 chance. When you start to add those together, what you do is you actually increase the prediction of those. And one of the ways we look at that is called accuracy, which is a combination of the sensitivity on the y-axis, the specificity on the x-axis. And here, what we're actually trying to do is push our models for prediction closer and closer to the upper left side of the edge here. And in this case, there's 3 different types of cardiovascular risk factor scores that are being compared here. And as you can see, the one in red here predicts better. It has a higher sensitivity and specificity across each of the aspects of it and a higher accuracy. This is important because the individual components of an index or a score can be used for both the clinical interpretation and messaging, as you'll see with cases that have been done very well and intentionally, like Life Simple 7, about controlling your risk factors. It's not about the risk as much as it is, these are things you can do. So this is great for public health messaging, and really one of the places where we want to take our risks and start to look at them in an implementation manner. So how are these developed? I really like this set of criteria. There's many different criteria that have been used, and this one from Social Research is actually very nice because it's relatively simple. The individual items that go into a risk score or an index are based on how well they relate to a construct. In the world of cognitive testing, we think of this in the way of domains. Cognitive domain of executive function. How well does this test? And do these tests together represent this? So there's this sort of construct or content validity that's necessary to consider when putting them in. Sometimes methods that are solely based on data and machine learning of data or AI may not be able to catch this content validity. And you may end up getting spurious variables that may be able to predict something about the disorder, but they're actually a surrogate for something in the construct that you're trying to get at. Another is unidimensionality. These individual pieces often aren't measured over time. They're not measured to represent different aspects of a disease process. They're snapshots in time. It's also important to understand, is this specific to a disease? In the individual items, do they relate to the disease specifically, or is it a general risk? So something along the lines of age, for age-related disorders, it's often one of the number one things, but in and of itself may not be as specific as individual measures that push someone towards a disease process. So we weight these things in the process of selection. Items should be empirically related to one another, which means they're correlated. They are related to each other through statistical methods, and therefore, when added together, they allow additional prediction of a process that you're trying to model. And the index scores are designed and determined by the index scores themselves get designed and scaled based on the way you want to represent them. So some of the ones that we'll talk about in cardiovascular disease might just be simple sums of scores. Do you have an abnormal value of cholesterol and blood pressure and glucose? Therefore, you've got a 3, as opposed to not having abnormal on any of them, and you're a 0 in every permutation in between. Others are based on weighting factors. Some of them are standardized, as we do with neurocognitive tests, and we might use z-scores and combine them together. What that does is that affects the type of scale. Commonly in cardiovascular disease, when we're trying to predict events, we'll look at how well does it predict your percent risk of getting an event in X amount of time. It's often 10 years. And so this range is really important for messaging, but is used later in the process. And most importantly, all indices should be validated through external prediction, whether that is the prediction of the presence of some form of pathology that we are interested in Alzheimer's and related dementia, predictive of cognitive decline, or events of conversion from normal to MCI to dementia. And this is really the rigor at which we should use when we develop indices. And we'll talk about some of the existing indices today that have been developed already in the context of cardiovascular disease and how they relate to Alzheimer's and related dementias through their relationships to cognitive decline, incident dementia, and even forms of dementia pathology. So here are a review of some of the common types of indices. You have risk factor composites. In cardiovascular disease, some of the ones that we look at are the Framingham risk score, some of Life Simple 7, which we'll talk about today, or metabolic syndrome. In and of itself, metabolic syndrome tells you more about the risk of someone developing diabetes than just their fasting plasma glucose. And that's one of the reasons why we put these together. These also may be indices that are compound measures representing some aspect of physiology. We won't touch on very many of these today, but in essence, if you're trying to look at a physiologic process and it's a combination and not a direct measure of a process, it allows you to understand some aspect of physiology, whether that's how stiff the arteries are, or whether or not that someone has lower extremity atherosclerosis in the case of ankle brachial index. So these are indices that are used to develop aspects and constructs of physiology. And I'll touch a little bit later on how that can be useful in our work. And then more recently, multidimensional data has been harnessed to start to develop things that are new risk calculations, new risk indices based on genetics, omics data, signal processing that can be used from continuous measurements where you're not looking at a single value of something, but the way that that value changes on a day-to-day basis at 1 minute increments over the course of 14 days. So it's just saying, here's someone's average glucose over 14 days doesn't, you're probably missing a lot of the complexity and usefulness of that continuous monitoring. And finally, in the context of Alzheimer's disease, we're actually used to these indices because things like the ATN framework are an indice. It's taking individual biomarkers themselves, like amyloid, tau, neurodegeneration, and putting them together in a construct to identify people who are positive on each of these formats or not, and to be able to look at evidence of this pathology. And the same is being done for evidence of small vessel disease on multiple aspects of the biology that we can see on imaging. So one way to think about this is that these can be useful to construct aspects of looking at pathways by structuring the physiology through indices that represent things like atherosclerosis, arteriosclerosis, cardiac function, to get at the cardiovascular side of things, and metabolic disease, to understand and to start to break apart the individual aspects. Or they can be aggregated together as they've traditionally been done to look at total vascular or metabolic risk. And these can be brought together along with what we can bring from neuroimaging and cognitive testing to start to understand pathways about how we expect vascular and metabolic disorders to be related to dementia-related pathology, and also to whether or not an individual is likely to have mixed forms of dementia that involve the overlap of vascular and Alzheimer's pathology. Okay, so let's talk about today. Hopefully that's given you an overview of what we'll be covering. And today we have two great speakers. Mike Bancks is an assistant professor here in epidemiology and public health science. And Mike has had many years of experience working with cohort studies and cardiovascular data, and also diabetes risk. And so Mike today will be talking about LifeSimple 7 as an indice, not just of cardiovascular disease, but also in dementia risk prediction. And then next we'll have Chris Schaich, who is an assistant professor in hypertension. And Chris has been working with us for a few years looking at individual vascular risk scores as they relate to cognitive decline and neuroimaging biomarkers in the MESA study. So before we jump into those, I want to review with you the goals of these talks. Today, we're going to review existing indices of vascular disease that may be able to be built from our existing data that we already collect in the ADRC. But to do that, we want to have you have an opportunity to contribute to questions at the end, where we'll be talking about, are these practical measures for us to measure in our ADRC studies? How do we choose what we want to construct? And what additional resources can we bring together on this topic? So without further ado, I will turn it over to Mike. And Mike, I'll stop sharing if you want to share your screen.
As Tim introduced, thank you. Thanks for inviting me to be here. So I'm here to talk about the American Heart Association's construct of ideal cardiovascular health, also known as the LifeSimple 7, or how they've summarized it as the LifeSimple 7. If you need to get a hold of me, here's my email. I'm in epidemiology and prevention here downtown. So what was the purpose of ideal cardiovascular health? So the American Heart Association put together this strategic task force where their goal was to come up with a construct that defines and measures cardiovascular health. What does that mean? What does cardiovascular health mean? And they did this because they wanted to have this construct to be able to monitor and improve cardiovascular health, not only among individuals, but also of the entire population. They wanted to be able to monitor cardiovascular health among the entire US population in order to reduce cardiovascular events by 20% and improve cardiovascular health overall by 20%. So it goes with their 2020 goals. That's how they got on 20. It's a thing they do. But what comprises ideal cardiovascular health? So there are 7 metrics that they use to define cardiovascular health. There's smoking status, diet pattern, where they emphasize consumption, greater consumption of fruits and vegetables, fish, whole grains, and then downplay or suggest not to consume large amounts of sodium or sugar sweetened beverages. Physical activity is another component, body weight, blood pressure, blood glucose, and blood cholesterol. So it's just these 7 metrics, and they chose these, one for ease of ascertainment and based on their individual associations with risk for cardiovascular disease. And if you intervened on one of these metrics, could you prevent cardiovascular disease? So the whole basis for these was these 7 metrics. They boiled down, all of the literature and said, these are the major primary measures that if we were able to intervene, we could alter the course of someone's cardiovascular health. So again, it's really based in, Tim talked about, the validity of a construct. Do they measure what your big picture, what you're trying to assess? And so the whole goal here was to understand or to try to characterize an individual's cardiovascular health profile. So what would you need? What kind of data would you need to operationalize this? So here are the 7 components. And then what they did is they determined an ideal, an intermediate, and a poor health status for each of the 7 components. And so in order to meet ideal, say here for smoking, in the last year, you had to have given up smoking in, beyond a year ago, or have been a never smoker. You would have been considered to have ideal cardiovascular health for smoking. An intermediate health for smoking would be you've quit, but it's less than a year ago. And then a poor cardiovascular health status just for smoking would be you're a current smoker. And so you can see you can characterize, or you can categorize ideal, intermediate, and poor health for each of the 7 characteristics. Blood pressure, blood cholesterol, and blood glucose all do take into account medication use. You cannot have ideal cardiovascular health for any one of those metrics if you're on medications, but if you're treated to a goal, you could be an intermediate health status. The whole idea here is primordial prevention of an elevated risk factor. And then, so when people are operationalizing ideal cardiovascular health or cardiovascular health score, they often do it as the total number of components that meet ideal status. So it would be a score of 0 to 7, or a total score. Here you can see they allocate 2 points for ideal, 1 point for intermediate, and 0 points for poor. So a score from 0 to 14, with a higher score being healthier overall cardiovascular health. So maybe aside from diet and physical activity, a lot of these are readily attainable in EHR. Maybe through additional questionnaires, you can ascertain diet and physical activity. So what does this look like in the US? So here on the key, you can see the number of metrics that are ideal. Here's percent of the population. This is NHANES data, so it's representative of our non-institutionalized population. These are just adults, so 18 and older. Here's 1988 to 1994, 99 to 2004, and 2005 to 2010. As you can see, a good thing is we have very few individuals who have 0 metrics that are ideal. So, there are very few individuals who are not ideal for any of the metrics, but also on the flip side, we have very few individuals who are ideal for all 7 metrics. You can calculate your own score and understand where you fall, but each of these metrics are associated with cardiovascular disease, particularly mortality and incident events. So here we're just looking at some, this is all mortality that we're looking at. So here on the y-axis, we have cumulative mortality. Here is all-cause mortality on the left, cardiovascular disease specific mortality in the middle, and then this is ischemic heart disease mortality on the far right. These lines represent the number of cardiovascular health metrics that you have ideal. So this 0 to 1 would be the worst or poor cardiovascular health. Greater than 6 would be ideal. So you can see a strong gradient regardless of what the cause specific mortality is, that a greater number of metrics that you have ideal cardiovascular health, a lower cumulative risk or a lower cumulative mortality, regardless if it's all cause CVD, all CVD, or ischemic heart disease. Looking at incident CVD events, here's data from our own study, ERIC. We're a field center here, as you may all know. Here again, we're looking at cumulative incidents, number of metrics that are ideal, so 0 to 4. And you can see that a greater number of ideal cardiovascular health metrics is associated with a significantly lower cumulative incidence of cardiovascular events. So major cardiovascular events of myocardial infarction, coronary heart disease, and stroke. How about other cardiovascular events, such as heart failure and venous thromboembolism? Very similar layout. Again, cumulative incidence here on the y-axis. Here we can see individuals with poor cardiovascular health. This is represented as the score. So instead of number of ideal cardiovascular health metrics, they scored cardiovascular health from 0 to 14. And we can see, so it's this group would be 0 to 4 would be their score. Here's people who scored 5 to 9, and then individuals who scored 10 to 14. There's 2 lines for each of those because they did a stratified analysis by race ethnicity, but you can see it's very consistent that individuals with poor cardiovascular health have a much higher cumulative incidence of heart failure than those with ideal cardiovascular health scores. Similar pattern for VTE. Here we're now looking at survival instead of cumulative incidence. So a line that is quickly decreasing would mean that there's a greater accrual of VTE. And here again, we can see those with poor cardiovascular health have a shorter or a lower survival than those with ideal cardiovascular health when we're looking at VTE. So really, regardless of what cardiovascular outcome you're looking at, this index or this composite is strongly associated with cardiovascular disease. But now, how does it fare with cognitive related outcomes? So here we've got Alzheimer's disease and related dementias, and then mild cognitive impairment. So if we just look at this top table, when you compare ideal to poor cardiovascular health, so maybe similar to this, where you've got a group of individuals who you categorize as ideal, and then a group who are categorized as poor. Those with ideal cardiovascular health have a lower risk for stroke, which is understandable. Marginally lower risk for all-cause dementia and Alzheimer's disease, and significantly or a strong association of lower vascular dementia. Here, this is when we're measuring ideal cardiovascular health near the time of our event. When we go back further in time and measure ideal cardiovascular health, and then look over a longer period, you can see the strength of association gets stronger. So this means that really shows that cardiovascular health earlier in life, when you measure it earlier in life, it has a stronger association with future events rather than cardiovascular health that's maybe measured more proximal to an event. So you want to have as much time as possible between your measure of cardiovascular health and your outcomes to really see an association. And it's probably because there's maybe some underlying reverse causation here. So here were different types of dementia. Here we just look at mild cognitive impairment. This is from the Regards study. Very similar story when you compare those with ideal cardiovascular health to those with poor. So here we're looking at a score from 0 to 14. We see a lower odds for MCI among those with ideal cardiovascular health. So almost 37% lower odds for developing MCI than those with poor cardiovascular health. This is just another way to look at it. This is from the Whitehall study, so a cohort from England. We're looking at cardiovascular health and incident dementia. Here's the distribution of cardiovascular health scores in this population. So you can see it's looks like a normal distribution, really centered around about a score of 9. And then you can see across this distribution, there's really a gradient. So going from poor cardiovascular health to ideal, we can see the hazards for dementia decrease across this gradient. What about just cognitive test scores? So here we're looking at cardiovascular health in relation to cognitive decline or repeated measurements of cognitive function. So here on the y-axis for this top graph, we've got global cognitive score, a standardized global cognitive score, and on the bottom graph is a standardized memory score, or memory domain specific. And both of these really tell the same story. So those with ideal cardiovascular health start with a higher score, but they have a less steep cognitive decline. You can see how close these lines are, or these groups are at the start. You can really see the spread over time, that those with poor cardiovascular health tend to decline in their global function, but then also in memory specific domains, they decline to a greater degree than those with better cardiovascular health. If we're just looking at cognitive scores based on cardiovascular health earlier in life, this comes from the Cardia study. So Cardia enrolled individuals who were 18 to 30 and then followed them and is still following them for now over 30 years. And so here, this year 0 and year 25 represent when cardiovascular health was measured. And then you've got cognitive test scores in these rows. So here we've got the digit symbol substitution test, we've got the Stroop test, and the Ray auditory verbal learning test. And you can see that, that across each of these tests, those with poor cardiovascular health score worse than those with ideal cardiovascular health. You can see that the association is stronger. So if you assess cardiovascular health earlier in life, compared to at the same point in time when cognitive function was assessed. I'm sorry, I didn't clarify that. You see a stronger association, meaning better cardiovascular health earlier in life is more strongly associated with better cognitive function than if you were to assess cognitive function really at the same time as you're assessing cardiovascular health. Here's just some cardiovascular health and cognitive function in the study of Latinos, or the Hispanic Community Health Study. Very similar story. When you move from poor cardiovascular health to ideal cardiovascular health, you see an improvement or better, higher scores of cognitive function. So here we've got the Spanish verbal learning test, the total score. Here's the recall specific domain. Here's expected word fluency, the digit symbol substitution test, and then here's a probability for scoring below a certain number on a screener. So a lower probability is indicative of better cognitive function. And so I've highlighted the blue line just because that's the fully adjusted model. You can see it's somewhat attenuated from a less adjusted model. But really in each case, we can see that across cardiovascular health, you've got better cognitive function test scores in multiple domains and overall. Here's some results on brain structure. So how does cardiovascular health relate to brain structure, measures of brain structure? So again, this draws from data on the cardiac cohort where they were young adults when we assessed cardiovascular health, and then we assessed brain outcomes later in life. So here we're looking at total brain volume, gray matter volume, and then abnormal white matter volume 25 years after cardiovascular health was assessed. And we can see when you compare ideal to poor, we see greater volumes of normal brain tissue. It's primarily through greater gray matter volume. And you see a lower odds for abnormal white matter when you compare ideal to poor cardiovascular health. Here is assessing both cardiovascular health and brain outcomes in young adulthood. So this study is among individuals who are 25 years old. And so you're already seeing a strong association among young adults with those who score with ideal cardiovascular health or higher cardiovascular health. They have higher vessel density, cerebral vessel density, higher caliber, and then fewer white matter lesions. So it's really, I mean, this is quite striking because you're already seeing an association early in life. If you look at cardiovascular health and brain structure in older adults, you still observe association. So when you compare ideal to poor cardiovascular health, we can see that there's a greater overall cerebral volume. So these positive numbers suggest that there's a greater volume per incremental or per additional ideal cardiovascular health factor. And we see lower abnormal white matter or white matter hyperintensity volume. And then this is just some more validation of that. This greater cerebral volume that we observed here, and then also previously in cardia, is really, again, primarily through greater normal gray matter volume. So sorry, I breezed through a lot of that just to get you an understanding of how it's associated, of how cardiovascular health is associated with Alzheimer's related outcomes. There's some limitations of the cardiovascular health score. Tim's touched on them. It is great that you want to construct an index of related items, but when you do that, you combine together metrics that are not independent of one another. So, we're talking about health behaviors that influence health factors or phenotypic factors. So of course, physical activity, diet, smoking are related to blood pressure, blood glucose, right? So you lose, there is a non-independence of combining those metrics together. And then the Life Simple 7 or the ideal cardiovascular health doesn't really weight. It applies a uniform weighting across the metrics. So here are two different two different individuals with the same cardiovascular health score, a score of 10, where they may have ideal, individual A has ideal health for physical activity, BMI, diet, cholesterol, and smoking, but then poor cardiovascular health for blood pressure and fasting glucose. That'd be the same score as somebody who has blood pressure and fasting glucose in the ideal range, but then cholesterol and smoking are intermediate and diet is poor. And, the impact of these being poor, their impact on disease may not be the same as someone who just has diet as poor, right? There is some definite differences in how each of these metrics impact disease. So that's just something to think about when you're constructing the score and using it. that was all I have. Sorry, I went through it, but I wanted to make sure I got through in time.
Thanks, Mike. And thank you for going through the various research that's related ideal cardiovascular health to both incident dementia of multiple different causes and also brain structure. And also thank you for pointing out the fact that when you build number of risk factor models like this, it fails to be able to allow you to tease apart the individual components, obviously. So a lot of times when we'll do models of these, we'll actually run the individual factors to see the contributions of those factors, because they aren't weighted in a manner of how they might be related to the disease. They're actually just weighted on is it abnormal or not? Great. So we will go ahead, and since these are related topics, we'll go ahead and move on into Chris's presentation, and then we'll have plenty of time at the end for discussion of these topics. So Chris, why don't you go ahead and share your screen and take us a run through some of the other cardiovascular risk factor profiles and how they've been related to cognitive decline and dementia biomarkers.
Okay, great. Well, thank you for the opportunity to present today. Today, I'll talk about the associations among vascular risk scores and cognitive performance, as well as some dementia-related neuroimaging markers within the multi-ethnic study of atherosclerosis. So the risk scores I studied included the Framingham stroke risk profile and the atherosclerotic CVD pooled cohort equation scores, which were both developed to estimate an individual's 10-year risk of having a CVD event or stroke. And I'm going to contrast these against another risk score, a dementia-specific risk score called the Cardiovascular Risk Factors, Aging, and Incidence of Dementia, or CADE, which was developed more to, predict incident dementia rather than cardiovascular disease. But really, it was also developed to integrate vascular, lifestyle, and socioeconomic factors that are known to be associated with dementia. So I just wanted to first compare and contrast those. And when we take a closer look at the individual components that make up each risk score, we could see that there is a lot of overlap among them, but each also has their own unique components. So all of them incorporate age, sex, and systolic blood pressure. The CADE uniquely incorporates BMI, physical activity, education level, and ApoE carrier status. At this point, I want to point out that the CADE and Framingham stroke were developed in mostly white cohorts. The CADE came from a Finnish cohort, the Framingham stroke, obviously from the Framingham cohort. The ASCVD was developed within several different, using data from several different cohorts that included more than just one race. So it's unique among these risk scores in that it does account for race. So the objectives of these studies were we wanted to know if vascular risk scores were associated with cognitive performance and dementia-related pathology. We also wanted to know if these associations were comparable, and furthermore, will they differ by race or ethnicity? Keep in mind that that the Framingham stroke and CADE were both developed in mostly white cohorts. So to investigate this, we used data from the multi-ethnic study of atherosclerosis. And I'll first just bring your attention to the timeline here to orient you. We calculated these risk scores using data from the baseline examination. Then at exam 5, approximately 10 years after the baseline exam, participants were administered a cognitive assessment that consisted of 3 standardized tests, including the Cognitive Ability Screening Instrument, or CASI, the digit symbol coding test, and the digit span. At exam 6, approximately 6 years later, a subset of participants were re-administered these cognitive tests. And among those who provided repeat CASI data, we also looked at the association with a greater than 1 race ethnicity specific standard deviation decline in CASI performance from exam 5 to exam 6, which we just defined as a measure of global cognitive decline. But first, we wanted to demonstrate that these risk scores vary across races and ethnicities, suggesting that the burden of vascular risk factors is not evenly distributed among races, with Black race and Hispanic ethnicity having generally higher risk scores compared to white across the 3 scores we studied here. And so then this is presenting the association of these risk scores with scores on the exam 5 cognitive tests. So to orient you, these graphs are showing the difference in each cognitive test score per standard deviation increment in each risk score. So one thing that's apparent is that there is an inverse relationship between risk scores and cognitive performance. The higher your risk, the higher risk scores were associated with lower cognitive performance. And this was significant across each cognitive test. We went ahead and compared, in comparing the magnitude of these associations, we found that with regard to the CASI, the CADE had a larger magnitude of association than the Framingham Stroke and ASCVD scores, as well as compared to the Framingham Stroke in the digit symbol coding and digit span tests. However, in those tests, the magnitude of association of the ASCVD score was comparable to that of the CADE. So we also tested for interactions by race and ethnicity, and we found highly significant interactive effects. And so I'm only going to show data from the CASI here, but here are the associations of the risk scores with performance on the CASI stratified by each race. And I guess the main takeaway from this is that we found that the associations of the CASI with the Framingham Stroke and ASCVD were of generally smaller magnitude in non-whites, but were actually larger in the non-white race ethnicities with respect to the CADE, which is just a little interesting note, since the CADE was one of the scores developed in a mostly white cohort. And so then we also looked at the association of these risk scores with odds of a standard deviation decline in CASI from exam 5 to exam 6 among the subset that had repeat cognitive testing. And we found that each risk score was significantly and comparably associated with a with greater odds of experiencing a standard deviation decline in CASI score over this time period. So then we looked at the association of these risk scores with some neuroimaging markers of dementia-related pathology. So this sample was also drawn from MESA. It was drawn from approximately 320 white and black Wake Forest site participants who were enrolled in two MESA ancillary studies. As part of these studies, a subset received brain MRI, and a subset of those participants received amyloid PET. So we were interested in the subset that received amyloid PET, so the markers we looked at included beta amyloid deposition, which we quantified by Pittsburgh compound B PET. We looked at its continuous standardized uptake value ratio. And we also looked at a couple of MRI markers, including white matter hyperintensity volume and temporal lobe cortical thickness. We found that risk scores were generally associated with these imaging markers. With regard to A beta deposition, we found that standard deviation increments in the CADE and Framingham stroke were associated with more A beta deposition, but not with respect to the ASCVD. We did find that all three risk scores, higher risk scores, were associated with greater white matter hyperintensity volume, as well as with lower cortical thickness. We also, again, examined interactions by race and ethnicity, and found that associations with cortical thickness and the Framingham stroke and ASCVD did differ by race. So here are those associations just stratified by race. We see that with respect to the ASCVD and Framingham stroke, our associations were really driven by white participants, whereas they were not as strong in Black participants. So to summarize, we did find that antecedent vascular risk scores were associated with dementia-related neuroimaging biomarkers. These associations were largely consistent by race, except for with respect to cortical thickness. We also found that these risk scores were associated with cognitive performance and risk of global cognitive decline. The associations with the CADE were generally stronger than the Framingham stroke scores, but the ASCVD and CADE were comparably associated with processing speed and working memory domains. And again, associations did differ significantly by race and ethnicity with respect to each test. So that's all I wanted to present. And at this point, I'd be happy to take any questions. I guess I should send the screen back to back to Tim and open it up for.
Thanks, Chris. And thank you, Mike, for presenting on these existing cardiovascular measures and how they relate to Alzheimer's and related dementias through the relationships with cognition, cognitive decline, and in some cases where they've been evaluated with actual imaging biomarkers. So we want to just in the few minutes that remain, we want to open it up for any questions that you might have about these factors. I think you can see some of the shared relationships between these factors. And then we'll summarize and talk about the next steps.
I see a question in the chat asking to see the last slide. Was that for me?
Let's assume so.
Yeah. Yes, please.
Thanks, Dory.
Tim, this is Lynn. I might just say while he's pulling those up, the thing that impresses me that Mike showed is that the data are stronger for measurements taken in midlife versus those taken more current to the outcome, which is great news for intervention, I think.
Absolutely, Lynn. I would definitely agree with that. And a lot of these cardiometabolic risk factors have stronger relationships to dementia and imaging biomarkers when they're measured in midlife. So some of the work that we've done in the ADRC study has shown that the midlife vascular risk factors and metabolic risk factors matter more. And as you get later in life, these markers change over time with aging, and some of them may decline on their own regardless of treatment.
I was going to say, Tim, just to follow on that, I think it's even a bit more complex than that, that they actually turn out, some of them, to have protective effects in late life. So a higher BMI is associated with reduced risk of dementia to a point, not morbid obesity, but overweight. And that a slightly higher blood pressure, again, not significantly hypertensive, but mildly hypertensive in an older, say, person in their late 70s and 80s is protective. And again, I think potentially because of compensatory changes that have happened that make it such that if you lower blood pressure in a much older adult, you might, the system has recalibrated. So anyway, that's a great point, and it is a very important point to keep in mind when you're applying these kinds of summary or combined indices. That the relationships of the individual components may be different in younger versus older adults.
That's right. Especially to clarify a piece on that, it's, as Laura put in the chat, the data also mentioned that it's never too late to begin to change the risk factors. And a lot of the people that Suzanne talked about that it looks like that the risk factors themselves are protective in later life. Those are often individuals who did not have the risk factors at midlife. If anyone had the risk factor at midlife and they still have elevated risk factors, they're in that risk factor bin where they are at a greater risk.
I think there's a duration of exposure factor. There's also a treatment factor, because as we know, some of the treatments for the conditions may have their own protective effects, and how well, and there also is one I don't hear people talk about, and that might be a surveillance bias factor, right? So you discover in midlife that you have hypertension and you're the type of person who pays attention to it, you may keep an eye on that, right? Whereas not everybody will do that, but for some people that might offer a heads up to focus better on better health from an earlier time.
I had meant to point out actually that I think it's important to note that sort of on the topic of it's not too late to start improving health, that these vascular risk scores have inherent limitations because they were developed retrospectively from cohort studies under the assumption of an unchanging environment. So they can't account for for medications, for interventions. So I think that just I think it speaks further to say that it's not too late to change your health.
So I realize that we're at the top of the hour. So I do want to share the sort of final slide about what's next. So in this series, this was to talk about existing mostly vascular measures. A lot of the same vascular measures include a lot of the metabolic indices that we're interested in. And you can debate on whether they're vascular or metabolic indices. The next piece that we'll look at in spring will be some of the more novel indices that are being developed for vascular and metabolic health. So we are inviting speaker recommendations on these topics. A few of the things that have been kicked around as potential invitations for speakers are some of the work that's being done on machine learning identification of cerebral small vessel disease and the combination of these individual forms of small vessel disease into an index that can get a better handle at the extent of vascular disease, particularly small vessel disease in the brain. Another is the use of continuous monitors. So a single glucose measurement can tell you something about a point in time, but during the day, glucose varies dramatically, not just with diet, but also with diurnal variations. And so getting an average glucose, I think you can see across the day, doesn't tell you the complexity of what's going on. So there's additional signal processing measures that can be done to start to look at the variability over time and also patterns of variability during the day. So if there are other topics that you think would be, that you know of, that you think would be wonderful for this novel indices, this is going to be really today was a setup for talking about these indices long term. So please let us know about speaker invitations.
May I have a quick question from Mike?
Go for it.
In the calculating of cardiovascular health, the scores that we were given to the total cholesterol and blood pressure, they were both without treatment. I was wondering that for the people who are on treatment, for example, for the statin or for the blood pressure medications, and they are in the normal range, they are not given even one score.
That's right. Yeah, they're the best they can score with treatment is an intermediate. Yeah, it's you're pointing out there's somewhat of a subjective categorization there because they don't really do the same thing with smoking. They allow you to be a former smoker. The evidence there suggests that with longer cessation of smoking, you can get closer to cardiovascular health of an individual who didn't smoke. Yes, there's a definite difference if you look at group levels, but yeah, that's a great point. That's a
yeah. Thank you.
Great talk, Tim and Mike and Chris. All of you did a really great job of setting the stage. And listening to you guys and thinking about what we're doing here at the ADRC, we have so many different endpoints that are relevant. I guess the question is, how do we make those decisions about what to include in an index? Or would it be feasible to think about setting up multiple indices? And how do we make ours novel than what's already out there and applicable to looking at aspects of Alzheimer's disease that other indices are not able to evaluate?
Great question, Sharon. And this is really intended to get the conversation started. So I think it's important that these risk factors, we use the ones that, one, we have data that we can combine into indices that may be more predictive than the individual factors that they have. And also that these factors are things that we can track over time to look at change in these factors. Next time we'll talk about the cutting edge of maybe there are additional metrics to add to these factors, because what we've talked about today are mostly just routinely clinically measured factors and make a basic assessment. Great. Well,
Thank you, guys.
we don't want to keep people too long today.
Yeah.
Thank you all for attending, and let's keep the conversation going on these, and look out for the invitation to the next in the series where we'll talk about these novel indices.